Imagine a beam of light, a phenomenon so common that we rarely stop to consider its remarkable journey. Picture a pure ray of sunshine, traveling millions of kilometers through the vast emptiness of space. This light leaves the sun and races toward Earth in a perfectly straight line, undisturbed by anything in its path. It takes just 8 minutes for sunlight to reach us, moving at the universe's ultimate speed limit, about 300,000 kilometers per second, a speed so fast it's almost impossible to truly imagine. But the story changes when light encounters something in its way. When it hits our atmosphere, or dives into water or glass, it slows down, as if the material is making it work harder to get through. The denser the material, the more the light is delayed, and the more its path is altered. This is what we call refraction. Light bends and slows as it passes through different substances, changing direction in a predictable way. It's why a straw looks bent in a glass of water, a simple trick of the eye caused by the bending of light. It's also why lenses help us see, focusing and bending light to bring the world into sharp detail. Our technology, from eyeglasses to powerful telescopes, and our entire understanding of optics, are built on this reliable, predictable behavior of light. Light enters a medium, slows down, bends, and then exits, taking a measurable amount of time to complete its journey. The cause, light entering, always comes before the effect, light exiting. This sequence is as fundamental as the ticking of a clock. You can't finish a race before you start it. Or can you? In our everyday world, this seems impossible. But the quantum world is a place where our basic assumptions are constantly challenged, and the rules we take for granted can be turned upside down. Physicists have learned to expect the unexpected when they study atoms and photons, where reality often behaves in ways that defy common sense. Yet even the most seasoned scientists were stunned by an experiment that seemed to flip the very arrow of time itself. Imagine witnessing a pulse of light leaving a material before it's even finished entering, a result that seems to break every rule we know. This isn't just bending the rules, it's rewriting them, forcing us to question the very foundations of physics. At the quantum level, the universe plays by rules that seem almost magical, where cause and effect can blur and reality becomes stranger than fiction. The experiment we're about to explore doesn't just challenge what we know. It forces us to rethink the very flow of time, and what it means for something to happen before or after. What if the effect could come before the cause? What if our understanding of time itself is incomplete? What if light could cheat the race, crossing the finish line before it even leaves the starting block? This is the story of a quantum experiment that defies logic, challenges our beliefs, and opens the door to a new understanding of reality. It's a journey into the heart of the impossible, where the boundaries of science and imagination blur, and it all starts with a single familiar beam of light, something we see every day, but which still holds secrets waiting to be discovered. Get ready to see reality in a whole new way, as we follow light on its most astonishing journey yet. To pull off this quantum trick, scientists needed more than just a block of glass. They needed a cloud of cesium atoms, cooled to temperatures just a fraction of a degree above absolute zero. Achieving such extreme cold is no small feat. It requires advanced technology and meticulous precision. At these ultra-low temperatures, the cesium atoms move incredibly slowly, almost coming to a standstill. This sluggish motion allows scientists to manipulate and control the atoms with beams of laser light, almost as if they were arranging pieces on a chessboard. This super-cold gas became the racetrack for a pulse of laser light, a place where the rules of physics could be bent and tested. Instead of sending in a steady, unbroken beam, the researchers crafted a short, precisely shaped pulse, a wave packet with a clear beginning, middle, and end, like a message encoded in light. The exact shape and timing of this pulse were carefully measured and recorded before it entered the cesium cloud, ensuring that any changes could be detected. Another laser, known as a pump beam, was used to prime the cesium atoms, putting them into a delicate and highly sensitive quantum state, ready to interact with the incoming pulse. This process transformed the gas into what's called an anomalous dispersion medium, a material that interacts with light in the opposite way to what we see in everyday substances, flipping the script on how light usually behaves. The stage was set, atoms were primed, the light pulse was ready, and the entire experiment was poised on the edge of discovery. With everything in place, the scientists fired the carefully shaped pulse directly into the heart of the cold cesium gas cloud, initiating the experiment. On the far side of the chamber, sensitive detectors stood ready, waiting to measure not just when the pulse emerged but also its shape, and any subtle changes that might have occurred. The team expected to see something strange, but the results they observed went far beyond their wildest predictions, defying conventional logic. The outcome of this experiment would soon echo through physics labs around the world, sparking debates and excitement among scientists everywhere. This experiment was about to challenge everything we thought we knew about the journey of light, pushing the boundaries of our understanding. What happened next would make even the most seasoned physicists question the very nature of reality itself. The quantum world was about to reveal one of its wildest and most astonishing secrets, forever changing our view of what is possible. The detectors blinked, their tiny lights flickering in the dim laboratory, signaling that something extraordinary was happening. A pulse of light had arrived, racing through the experimental setup with astonishing precision. Scientists checked the timing, carefully analyzing the data on their screens. To their amazement, the peak of the light pulse exited the cesium cloud before the original peak had even finished entering. It was 62 nanoseconds early, a result that defied their expectations. Imagine throwing a baseball at a wall and seeing it emerge from the other side before it even hits the front. That's how strange this result seemed. It seemed to violate causality, the fundamental idea that a cause must always come before its effect, a cornerstone of physics. But the experiment didn't actually break the speed of light, the ultimate cosmic speed limit. The very front edge of the pulse never traveled faster than light. That crucial boundary remained untouched. Einstein's speed limit was safe, his theory of relativity still unbroken. What changed was the shape of the pulse itself, not its speed. The cesium gas acted like a quantum funhouse mirror, distorting and reshaping the pulse in a way that seemed almost magical. The atoms, primed by the pump beam, used information from the very front of the pulse to reconstruct a new pulse at the exit, almost as if they were anticipating what was coming. The peak that emerged was a forward-shifted copy, not the original pulse itself, but a clever reproduction. No information or energy actually traveled faster than light. The laws of physics remained intact. The light didn't time travel, but it performed a quantum sleight of hand, fooling even the most seasoned scientists for a moment. The result, a perfect illusion of impossible speed, a reminder that in quantum physics, reality can be stranger than fiction. Let's return to our running analogy. Imagine a marathon where the first runner's patterns are analyzed and instantly sent to the finish line. Clone runners at the finish use this info to form up and cross before the originals arrive. That's what happened with the light pulse. The front edge entered the cesium gas, and the atoms read its shape. Using stored energy from the pump beam, they built a new pulse at the exit, before the original peak arrived. No photon broke the speed of light. The information about the pulse's shape traveled at or below light speed. The experiment used the wave's shape and the medium's energy to create the illusion of impossible speed. It wasn't teleportation, it was quantum mimicry at the finish line. The quantum world had pulled off a remarkable trick. This result forced physicists to confront the weirdness of quantum theory. Our belief in causality runs deep. Effects shouldn't appear before causes, but in the cesium gas, anomalous dispersion reshaped the light pulse, advancing its peak. The math works, but seeing it in the lab is another matter. The effect was extreme. The output pulse existed before the input peak arrived. This challenges our definition of a light pulse. Is it a collection of photons or a pattern of waves? The experiment suggests the pattern is fundamental. The cesium gas didn't speed up the pulse, it manipulated the pattern. Information from the front was used to regenerate the peak further down the line. In the quantum world, information and energy can behave in ways that defy classical intuition. This experiment doesn't break physics, but it stretches our understanding of reality. The speed of the front edge of a signal can never exceed light speed, but the group velocity, the speed of the pulse's peak, can. No information or matter traveled faster than light. What's challenged is our mechanical view of the universe. Quantum mechanics shows reality is governed by waves, probabilities, and strange connections. The light pulse and cesium atoms became a single, interconnected quantum system. The result hints at non-locality, parts of a system influencing each other instantly. The pulse's information is spread out and processed in a distributed way. The experiment made a shape appear earlier than expected. Not a thing travel faster. In physics, such distinctions are everything. Reality is a story of patterns and information, not just objects moving through space. While time travel is off the table, this quantum magic could revolutionize technology. Controlling and reshaping light pulses could transform optical computing and telecommunications. In optical fibers, this physics could counteract data distortion, keeping signals sharp over long distances. The result: faster, more reliable global communications. Mastering these quantum tricks gives us new tools for quantum technologies, like ultra-sensitive sensors and one day quantum computers. Studying these exotic states of matter deepens our understanding of the universe. The direct tech may be years away, but the knowledge is priceless. Today's quantum experiments are planting seeds for tomorrow's breakthroughs. Why does this experiment matter? Because it shifts our perception of reality. Science seeks to demystify the universe, but this experiment reminds us that reality is stranger than we imagine. It forces us to question basic assumptions, like needing to arrive before you can leave. This process of questioning drives scientific progress. The experiment connects to the biggest questions. What is time? What is causality? What is reality's texture? In the quantum realm, past, present, and future can intertwine. Ultimately, this discovery inspires wonder and curiosity. The universe is still full of mysteries waiting to be solved. We started with a simple picture of light, but quantum mechanics shattered that simplicity. The cesium experiment showed a light pulse's peak can exit before it enters, without breaking any laws. It's a quantum trick. Atoms read the front of the pulse and reconstruct a new one at the exit. No particle breaks the rules, but the pattern advances in time. This challenges our notions of cause and effect and hints at future tech breakthroughs. Fundamental research expands what's possible and deepens our wonder. Even familiar things like light hold deep secrets. The universe isn't obligated to make sense to us, but it rewards curiosity. We've only begun to uncover its magic.